At Cepeo, New Mexico, I was using a 22-inch scope with a 1 degree field of view, and just for a point of information, I measured the Andromeda Galaxy as apparently about 6 degrees.
Okay, yes.
Okay, it
yeah,
came
so
close to 6 degrees.
Yeah, absolutely. So it's one of these things that, I mean, it goes out
Much
very,
further.
very far indeed.
Yeah.
So again, it
Now-
depends upon how well you can take the image to see how far out you can actually trace the light. So yes, that doesn't surprise me. That's
Yes,
very
I've got
good.
2 questions here. I understand that the Andromeda Galaxy is just slightly larger, apparently, than the Milky Way has been calculated, but the Milky Way supposedly has more dark matter or more mass to it than the Andromeda. And then also that the Milky Way has a bar in the middle, a small bar. Now, would a small bar be indicative of some cannibalism going on or prior collisions?
Yes, so for your first point, the Andromeda Galaxy is more luminous, so there's more stars and gas in it in total than the Milky Way, which to most of us would suggest is probably the more massive all round, to which it might be. Currently, the measurements of the dark matter mass of the M31, the Andromeda Galaxy, that we can do, and the accuracy to which we can do it, and the same kind of measurement for the Milky Way, are such that either might be slightly more massive than the other. At the moment, the uncertainty on those measurements isn't good enough to actually say definitively that Andromeda is more massive, but all of the pointers point to it probably being more massive in the dark matter, but there's uncertainties on that. Regarding the second point, yes, so in fact, the whole reason why some galaxies have bars in them, so basically the central regions where you have the bulge in a disk galaxy, sometimes that actually looks more like a bar, more like an elongation. And bars may be generated via a variety of processes, we think, one of which is absolutely correct, a merger, basically doing something to perturb the overall mass distribution, and that produces an instability which then generates a bar. There are other ways that perhaps don't require an interaction, but it's thought that an interaction may well trigger a bar. Yes?
How do supermassive black holes map with dark matter? And are there supermassive black holes in dwarf galaxies?
Sorry, I can't even see where you are. Oh, yes, sorry, hi. Supermassive black holes, how does that map with dark matter? Inside big galaxies, we believe that there are supermassive black holes. There's very, very strong evidence for it inside our own galaxy, because right at the center, we can actually see the stars that are right at the very center of the galaxy moving around incredibly fast. And the fact that we can see that implies that they must be moving incredibly fast. And the only way to do that we understand, is to have an awful lot of mass inside a very, very small area, i.e. a black hole. So we believe that big galaxies do have supermassive black holes. We think as well that the growth of galaxies probably also means a growth of that black hole. Sometimes because two galaxies with two massive black holes merge together, and eventually you might actually get the two black holes coming together to form an even bigger black hole, and you may actually have a lot of the material that was in the vicinity of those supermassive black holes falling into the black hole and making an even bigger black hole. In terms of whether or not smaller galaxies have black holes, that is still an open question. There is no strong evidence yet that these, certainly the faintest dwarf galaxies, there's no evidence yet that there's black holes in them. Doesn't mean there's not, but certainly there's no evidence that there is. At some level, galaxies seem to stop having central black holes, so the evidence for them having black holes seems to go away. And that's probably something to do with, well, how do we form black holes in the first place, or ones this size, and that's not actually something that's known either. But yeah, so the overall growth of a supermassive black hole is related somehow, we believe, to the growth of galaxies, specifically much more uncertain.
How do you feel about the Rees-Silk model of where the black hole forms first and then the stars and galaxies the size of the Milky Way and so forth?
Yes, it's entirely possible. With all of these, there's a lot of different types of predictions for when the black hole forms and when parts of the galaxies form, which may or may not be associated with the formation of the black hole. And at the moment, I'm unaware of sort of ways of distinguishing between these models. And so again, I like to sort of try and be as observationally motivated, i.e. what do we actually see? And so until we actually know sort of, in this model we expect to see this, and in this model we expect to see that, so there's something to go out there and test. At the moment, I'm ambivalent towards it, I guess. But the point is, it's an entirely reasonable thing. Perhaps the very first things to form are, in fact, very, very massive stars, what we might call population 3 stars, and perhaps those leave quite massive black holes in their wake, and perhaps that's the seed for everything that comes after. At the moment, it's an area of research which is just really being investigated now, so it's very uncertain.
Okay, we're going to take 2 more questions. Do you have one over there?
Yes.
Okay, and then we'll have one here.
Okay, so I think, if I understand what you said, the Andromeda Galaxy is going to collide with the Milky Way, but you said it's not for about 5 billion years.
Yeah.
About how old is the Milky Way galaxy, and does our sun even have 5 billion years?
So I showed that slide once to a school group who were visiting the institute where I work, and I hadn't really realized that they were very little kids. So I was talking about how in the end our galaxies are going to merge, and they were like, "Oh, does that mean we're all going to die?" I was like, "No, it's 5 billion years." And then I said, "Don't worry, the sun will be dead by then." And that for some reason that didn't have the soothing effect that I expected it to. So the sun is more or less middle age. Our galaxy, again, so it depends what you mean by the Milky Way. So as you can see, for example, eventually the Milky Way is going to be a much bigger galaxy called an elliptical galaxy, which might be called the galaxy formerly known as the local group. So the Milky Way has been around in some form for a very long time. That has now been put together in the way that it is. It's been more or less the way it is, we think, for several billion years. There hasn't been much going on. It's just been sort of fairly passive compared to a lot of galaxies, we think. So it's been around in some form for an incredibly long time, and probably around in its current form for several billion years. Our sun is middle-aged. It has 4 or 5 billion years left before it starts evolving, becoming a red giant branch star, and then a white dwarf, and then cooling away, et cetera, et cetera. Hopefully we'll live on a different planet by then, around a different star, maybe even in a different galaxy. That would solve a lot of problems, but we'll see. Yes.
One of the unanswered questions from your talk, I'm afraid, is why is so much dark matter associated with the dwarf galaxies? Maybe, up until an hour ago, I always assumed that the amount of dark matter in a given region was predictable by the amount of ordinary matter in that region, and apparently it's not by a factor of 100 or so.
Yep.
So the question arises, where is all this coming from?
Yep.
And if the big galaxies are, if clusters consisting of one big galaxy and several dwarf galaxies are formed by the merger of several dwarf galaxies, then the question comes up about the interaction of dark matter with dark matter and dark matter with regular matter.
Yeah.
Do they go through one another? Do they interact with one another, and so on?
Yeah.
And I think the conclusion that I'm reaching from what you said is that a cluster composed of a large number of dwarfs with a big galaxy probably has a continuum of dark matter spread over the whole cluster. And it's not that the dwarf is associated with a lot of dark matter, it's associated with a lot of the dark matter that's really associated with the big galaxy, rather than with itself as a dwarf. Could you comment on this enormous amount of dark matter?
So to go to the first point, yes. So dwarf galaxies have far more dark matter than you would think. Now, why is that? Again, this is an intense area of research. What we think is it's to do with the ability of a galaxy, of a dark matter halo, to form stars. That is to say, think about a low-mass dark matter halo, i.e. something that a dwarf is going to form in, compared to a much bigger galaxy. Much bigger galaxy, much bigger dark matter halo, is going to create, lots of gas is going to fall into it, it's going to have lots of stars form. When stars form, some of those stars are very massive and some of them go supernovae. Okay, now that basically explodes as a big shock, and it actually sends a lot of gas in the vicinity flying outwards. In a big galaxy, that doesn't matter so much, because it might send it flying outwards, but it's not sending it flying outwards so much that it escapes the dark matter halo. In a small galaxy, if you have some gas falls in, forms some stars, then some supernova goes off, this much lower mass dark matter halo is unable, we think, or potentially this is one of the reasons it's put forward, is actually unable to then hold on to the gas which the supernova is trying to send out. So it's what we call feedback. So basically the formation of stars in the first place then stops the formation of subsequent stars. because the gas that's required to form those stars blows out. So we think it's probably to do with the detailed interplay between the feedback effects, how the galaxy gets its gas in the first place, and then how it retains that gas once stars start forming, etc. To your second point regarding dark matter interactions, etc., this is a great point. Dark matter particles may be passing through us right now, and we would never know about it. Some guy was once describing it to a bunch of kids as if I had a dark matter gun that fired dark matter bullets. Those bullets would go straight through you, and the kids absolutely loved it. And so they're like imagining dark matter guns. But the point is that dark matter doesn't interact. The only way dark matter interacts is gravitationally, okay? Which means that instead, when I slap my hands together, they don't pass through each other, okay? Because there's lots of other forces at work that stop that from happening. That is not going to be the case with dark matter, and you would pass through each other. Whether or not dark matter can interact with dark matter depends upon what the dark matter is. But again, this is something that's being looked at. And finally, sometimes you're absolutely right. The dark, in terms of whether the dwarf galaxy is associated with its own dark matter halo, or whether it's actually just associated with all of the other dark matter that's going on, that's around the bigger galaxies. In that respect, that's what you say is sometimes correct. For the most part, you do seem to have coherent blobs of these subhalos in which the dwarf galaxies are forming, and depending upon how messed up because of tidal effects, gravitational effects happen, then the dwarf galaxy might get pulled apart, and in the process lose the dark matter that's associated with it, such that it becomes more associated with just the galaxy as a whole. So, but for the most part, dwarf galaxies are generally associated with their own clump of dark matter embedded within an even bigger clump of dark matter. So it's kind of both things at once.
Well, Dr. McMonaghy will join us if you have further
Absolutely.
questions right next door. You're welcome to join us for some refreshments. Also, give Dr. McMonaghy a great hand. Thank you so much for coming.
Thank you.